So yeah, we're going to talk a little bit about dynamic and static analysis and the trade-offs between them. Then we're going to go on to data flow and taint analysis, intermediate representations of assembly language and why it's useful. At that point, we're then going to go more into building logical formulae to express the semantics of assembly code and why that's useful, and then solving these formulae and how it can make reverse engineering a little bit easier. So exploit development, I guess there's two things. There's creativity in terms of trying to outthink whoever implemented protection mechanisms, trying to outthink operating system designers, but there's also tenacity in that you spend a lot of time just staring at a debugger, staring at dumps of assembly code and control flow graphs and that kind of thing. And realistically, to get better at this, we need better tool support. So everybody loves IDA, but it's just a representation of the underlying code rather than helping you understand the actual code semantics. And that's really what my talk is going to be about, trying to automate a lot of the understanding of the actual semantics of code rather than just disassembling and displaying it. So depending on how we've actually found vulnerability, our mechanism for constructing an exploit and our workflow tends to differ. So fuzzing, a lot of times we're essentially left with an input file that causes the program to crash. It's not really, you don't really know anything about the semantics of the actual application, what it does with that input, and it's from that point onwards, you're just running the program over and over again, trying to reverse engineer the important functions, trying to get a grasp on why it is that your particular input causes the program to crash. Other vulnerability discovery mechanisms tend to have similar workflows, I guess. You spend a lot of time staring at assembly code and just trying to figure out what the hell's going on. So this little guy, I think, expresses it pretty well. You're basically sitting all day in front of a computer, staring, running code. He's awesome, isn't he? And yeah, it's something a lot of times that I think we can do better at in terms of tool support. So if we think about fuzzing, for example, essentially a roller coaster of fail. You fuzz for a while, you find loads of crashes, you think, yes, I am definitely going to have like O-Day in the next half an hour. Realistically speaking, not so much. I mean, yeah. Let's just look at that for a little bit. So you have a lot of questions to answer, even once you have a crashing application. Why did the crash occur? Where did the data come from? Is this data even user influenceable? What conditions are on that data? So just because you have like 41, 41, 41, 41 in EIP doesn't necessarily mean that you can make it anything but 41, 41, 41. There could be all sorts of conditions imposed that force that data to equal that exact value. And without reverse engineering all the functions that data has passed through, you don't realistically have any other option if you want to write a reliable exploit. And yeah, figuring out what computations have been performed on your input data and whether, when a crash occurs, finding essentially every buffer in memory that's user influenceable in any way and how you can actually influence it. So other other bug finding mechanisms, I don't have any screenshots or photos for this, unfortunately. So just basic reverse engineering. What the hell does this function that does a pile of arithmetic modification actually do? Like semantically, what does it do? Not just understanding an add or a mul or a sub, but what is really the meaning of this code? Even basic data copying. So if you have like 150 moves and LEAs and that kind of stuff, it's not complex. The instructions, their semantics are very simple. But actually trying to figure out the relationship between input data and output data is non-trivial. So a general reverse engineering problem is, given we have a function, can a variable, we call it x, have a value y after a given instruction sequence? Tends to be a lot of what we do. So this is simple. This is out of BinNavi. Consider we want to know, just say we want EX to be the value 10. We can control the input registers. Okay, that's fine. It's not hard. It's 4 or 5 instructions. Still, can anybody tell me what instruction? Is the question clear? We want the value 10 written to the address pointed to by EX. Nobody? Okay. This This isn't complicated. There are no branches here. This is simply moves, mulls, and that's some shifts. Not complicated. This is what we do all day, every day. And yet, looking at that, you're like, great. Again, we have to do this. That code was actually from this code, which is a tiny little bit of the graph at the back. Again, very few branches. Realistically, considering what our job descriptions are, this should be quite simple to do. If we control the pointer in EDI, tell me at the end all the values or all the registers that are tainted by that initial input. By hand, this is not fun. And we seem happy to do this every day, basically. So current tool support, disassemblers, debuggers. We have manual static analysis platforms that nobody really uses. We have scriptable debuggers and static analysis tools, and we have instrumentation frameworks. Realistically, none of these provide a whole lot of automation in terms of actually understanding code. They represent the underlying code, but they don't really give you an understanding of what it does. So this is the problem statement, basically. Given an arbitrary point in a program, a collection of memory locations and registers, are those locations tainted by user input? So given that we control the entirety of an input PDF file at point X in a program, is the register EAX under our control? What exact bytes of user input? So if it's an addition of like 14 different bytes from user input, you want to know that it's those 14 different bytes. What computations have been done on these bytes? So just because a byte doesn't look like it's under our control doesn't mean that it hasn't just had like the value 4 added to it, which realistically is still completely under our control. What conditions, so compares, tests, etc., have been imposed. And bonus round, this is really where the theorem proving stuff comes in. Given this memory location with the value y, automatically generate an input that results in the value x at this location. So how does this help? Basically, this is what I was talking about earlier. How much of our day-to-day lives basically involves staring at shell code or staring at disassemblies, trying to figure out what are the bad cars for our shell code, what mangling has been done in input data, what are the bounds on write for addresses, and what are the bounds on any variable, basically. So realistically, I guess it's a high level 2 problems. Where's the data coming from? What conditions are on it? And what input do we need to drive it down a different path or to have different values? I apologize I'm going through this slide so quickly, but I think we're a little short for time. But if anything's unclear, stop me, ask me. Okay. So this is the basic agenda. We're just going to jump straight now into static versus dynamic data flow analysis. When people write tools, typically this is what they ask first. It's, do we want to analyze a program statically or dynamically? Realistically, for a lot of problems, what you want to do is you want a combination of both. So static analysis can improve dynamic analysis can improve static analysis. But depending on the amount of time you have available, this isn't really always viable. So static analysis, we're typically analyzing code without running it. It's imprecise by nature just because of the nature of computation. There's a huge amount of undecidable problems, things that we can't answer specifically. Solving undecidable problems, we typically have to give conservative answers if we want to prove safety, which means we over-approximate the range of values, we over-approximate the paths that can be taken. Essentially, we end up with false positives. The alternative is unsafe analysis, which is often acceptable, which means we have false negatives. So we under-approximate the set of values, we under-approximate the paths taken. And the bonus, or the good thing with static analysis, you can talk much more generally. You can talk about all paths in a program, or you can talk about like all variables in a program. Whereas with dynamic analysis, you're analyzing a single run of the actual application. So you're restricted to that particular run. You can typically only ask questions about the code that has been executed rather than theoretical paths that might be executed for obvious reasons. It's more precise by nature in that you can pretty much guarantee that if you see a value on a run of a program, then that value can be there because it is. Downsides, program lag. You typically do this at runtime. So if you're trying to analyze a time-sensitive property or a race condition or something like that, it could really mess with your day. Analysis storage. This tends to be a pretty big problem if you try to do anything complex with data flow analysis, in that you quickly, like even storing the addresses executed in memory, trying to record a full path quickly becomes into gigabytes of memory. and the generality of your results. Basically, as I said, you can only talk about the paths that you can execute. So making a choice, it depends on the task you're addressing. If you're trying to replace a human, then dynamic analysis probably isn't for you due to the aforementioned conditions. If you're assisting a human, then dynamic analysis is pretty good. I mean, you can use a human to make judgments about whether you need to execute new paths. You can use it, or you can use a human to guide the executed paths. And it also comes down to the frameworks available versus the frameworks you require. So for dynamic analysis, the actual engineering involved in building these tools is a lot simpler than for static analysis, and there tends to be a lot more available code. And the time allocated as well. Writing dynamic analysis tools really takes a much shorter time than static analysis generally, if you want to do it properly. So this is essentially why, for the task at hand, I decided to go with dynamic taint analysis. Why did I put that in the top slide? Okay, so dynamic analysis, basically, we want to instrument a program first of all. This is essentially, we want to insert our analysis code into the execution stream. Typically, we can use a tool like Pin or DynamoRio to do this. Essentially, what they do is they hijack control of the program at an early stage, and then if you want to instrument at the basic block level, they essentially take the basic block, insert your code before or after it, and then run the code on the CPU. This is why it's slow, basically. On top of this, we can build data flow tools. Obviously, if you instrument at the instruction level, before every instruction executes, these tools allow you access to the registers, the memory of the application. They allow you access to signals and threading events. So you can tell everything that is going on in an application. Once you want to do data flow analysis, you run into a problem, though, and that is the actual semantics of instructions. So it's quite easy to get access to an add instruction. You can get access to the first and second parameters, but actually figuring out the semantic relationship that this is in fact an add instruction, what it means for it to be an add instruction, is something that's typically not provided by your standard debugger or your standard or instrumentation tool. So, apologize for the amount of text in this. Essentially, data flow analysis is you're expressing the semantics of an instruction in terms of an abstract model of registers and memory. Your input basically is an assembly instruction. You have a model which says that previous to this, EBX contained this abstract value, ECX contained this abstract value. We now want to add them together. We update our model to reflect the fact that there is now a new node which represents the addition of two previous values in our graph. In its pure form, if you just did data flow analysis on everything, you would have a history of every byte in memory in terms of all its parent bytes, all its parent computations. Just to give a basic example of what I'm talking about. So these are 2-byte registers. Obviously, the numbering here will be relevant later. Basically, once you convert data flow analysis to a graph form, you actually lose the ordering that the instructions were executed in. So a typical approach to this is just to assign a unique ID to every node, so you know that if a node has a higher ID, then it was created after in the execution stream. It's pretty simple. So we encounter an add bx ax, we create a new node. We maintain the semantic relationship like addition or plus or whatever in this case. And when we have a sub, we update it again. And essentially, it's trivial. Like conceptually speaking, doing this is trivial. At this point, if we want to express the meaning of that 12 node, we know that it is the subtraction of the 9th node and the 6th. And we know the 9th node is the addition of the 0th and the 3rd. So we have a complete history in terms of computation of where this node actually came from. Taint analysis is basically a specialized case of data flow analysis, purely because trying to do data flow analysis over all executed instructions and all input bytes is it's practical, it's unnecessary. So with taint analysis, we basically start off with, we have a set of tags. Basically, we mark nodes as tainted or untainted. These nodes map to memory addresses and registers. But we also track the way in which a node was tainted. So we track the addition or subtraction. We initialize this tainted set basically by hooking reads, receives, receive from, system calls like that, or alternatively higher level wrappers. So basically what you do is every time you see a read instruction, so if it's a read reading in 1024 bytes, you create 1024 new byte nodes in your abstract model. You mark them as tainted by user input. Then every computation that these addresses occur in from then on until they become untainted, create new tainted nodes. Why we tainted the byte level? So some people have done it at a higher level. Realistically, you lose. So if you do it at a D-word level, you lose precision to a point that it becomes annoying. If you try to do it at a bit level, basically, you run into storage issues, and the slowdown, which typically is like a factor of maybe 50, can run into thousands. We also have to consider here indirect tainting, which is if you have a test basically between two tainted values, do you consider the flags that are set as a result of that to be tainted? And then do you consider the path executed once those flags are read to be tainted? So essentially what we're asking is, do we maintain the relationship between user input and the actual executed code? Which is a different problem realistically than tracing the actual semantics, but it's one that's useful as well. And then we also have indirect tainting. So if you have tainted data and you call string length on it, do we consider the return value, which isn't actually a computation directly based on user input, do we consider that to be tainted by an attacker? Or you can, if you want. So how do we propagate taint information? Basically, all this slide says, this was cut from a far more academic presentation, I apologize, is that a value is tainted, or sorry, a abstract location is tainted if any of the sources are tainted. So if you're considering flags, you would also consider the flags in this. Typically, it's if you have an add AX, BX, if either AX or BX are tainted, then you consider the resulting value stored in AX to be tainted. If neither are, which is the alternative, then you untaint that value. It's pretty simple. So we're not simply maintaining a set here, we're also maintaining this precise arithmetic relationship between nodes and previous nodes. So this is what we come to, basically. Where do destinations and sources come from? And where does this precise arithmetic relationship come from? The reason we have these questions it basically comes back to what I mentioned earlier about debuggers and disassemblers. It's very easy to represent, like in ASCII on screen or whatever, the fact that whatever bytes equal this instruction, this is how you interpret them. You know how to interpret them as a human. To actually interpret them for a computer, we need to provide the actual semantics of an add instruction, or a sub, or a mul, or whatever. So to do that, basically, you end up falling down a bit of a rabbit hole where writing trivial data flow analysis tools without this kind of thing is quite simple. You'll do it in a couple of hundred lines. Writing it with an actual semantic understanding of the code, you start to run into thousands or tens of thousands, unfortunately. So modeling data flow semantics, we can't automatically build this from parse tables, so basically we're left with the rather annoying choice of modeling each and every instruction in terms of what it means for this operation to be applied to our graph. So we're no longer talking about interpreting an instruction on a CPU, we're talking about interpreting an instruction on our abstract data flow graph, which represents the history of bytes and all that. So intermediate representations come up pretty quickly once you start talking about this kind of stuff. Basically, if you want to write analysis code and express the semantics of x86 or whatever, you quickly run into the fact that every x86 instruction actually has a couple of different writes or write destinations. Not every, many do. So you have flags, you have the explicitly mentioned registers, and you have implicit registers. To do this on x86, you quickly run into having to hack on special cases to consider all these extra flags. So an add is no longer just a simple addition of two values. You also have to consider the flags that are set. And on top of this, if I write an analysis algorithm for x86, and I then want to run that analysis algorithm on ARM, do I realistically want to rewrite the analysis code, or do I just want to rewrite a transformer from ARM into a different language on which our analysis code is written? And we can also build in, if we write an intermediate representation, we can build in properties such as static single assignment form, which is essentially the unique numbering of nodes, or we can also build in functional semantics. I'm not sure if I made it clear at the start what an intermediate representation is, so it's on the next slide, that's convenient. Essentially, this is from Valgrind. In this case, they don't actually, or in this example, the flags aren't expressed differently. They're basically representing an add as a retrieval from two registers into two temporary variables, an addition of these two temporary variables into another temporary variable, and then the storage of this back into 0, which represents the EAX, or EBX in this case. So you can quickly see that, one, you have a reduced instruction set because you can represent a lot of arithmetic instructions via a combination of others. But you also have a blow up in the amount of code you have to analyze, so it's a bit of a trade-off. So there's like a one-to-many relationship between the native instructions and your intermediate instructions. Once you start talking about this, this is the syntactic component, basically, the transformation of the assembly code into, this is the rail, or real, intermediary language from Dynamics. Almost all of those instructions, except for the very last one, are representations of the add. So it's one-to-many relationship, and you can reduce the instruction set you have to deal with purely because you can express other instructions in terms of many intermediary instructions. So this is essentially our syntactic transformation. Where this comes into play is when we're handed a chunk of code to do data flow analysis over, we essentially want to run this conversion on it. So we essentially end up doing data flow analysis over an intermediary language. This doesn't really get us, though, towards an actual an understanding of what those. I like that this guy's asleep. This doesn't get us towards an understanding of the actual semantics of an instruction. And for that, we basically move on to expressing what it means for these intermediary instructions on terms of the data flow itself. So this is, to be honest, the only way I could think of to represent it. Basically, understanding semantics basically is you have an abstract model, which is, can you guys even read that? Okay, so we have like this TMGR thing, which represents like a tainted manager, which maintains like a massive map in memory. Essentially, we express a move instruction, in this case, from register to memory as a direct copy, which is that direct copy. It's an assignment operator between two nodes retrieved from a graph. That's essentially what it is. You're manipulating a graph that you've built in memory. You can represent it as a map or whatever. So our analysis flow up to this point is basically we have an executing program. We have an instrumentation layer provided by PIN or Dynamo Rio or something like that. We have a syntactic assembly transform into an intermediary language. And then we apply the semantics of these instructions to an abstract model. Why is this useful? At this point, if you can implement this, and it's a bit of effort, but it's by no means prohibitive, you can directly answer then what bytes in memory are tainted by user input. Those are essentially the edge nodes of your graph. So, which are nodes that have recently been, or will have been created as a direct expression between user input bytes. We can also answer the next three questions, which exact bytes of user input, by tracing the graph backwards, back up to the source nodes. If you remember the example earlier, every time you create a source node that you don't have a direct representation for, essentially it's a graph with no or a node with no incoming edges, so all of those will be controllable by user input, presumably. And you can also answer the computations that have been done on these bytes, essentially by tracing edges. So previously we encountered the addition instruction, adding that little plus. Basically, you would store that in a class or a struct or whatever, that this was an addition that created this node. And we can also retrieve conditions. I didn't actually show that in the previous graph, but essentially every time you encounter a conditional instruction, or sorry, something that sets flags, You record the sources and destinations that set that flag. When you encounter a jump, you then retrieve the flags that have been read to affect that jump, and those are the variables that are constrained. But to actually do things with this, we need to process this graph that we've constructed after execution is finished, or once we've paused a debugger or whatever. So this is typically called a path condition, which is basically just a path through your graph that represents all the executed code so far. Basically, it's expressed as follows. This is more of a, I guess, practical than an abstract example. You declare all your nodes, typically as depending on the size of the register or memory location they represent. At that point, you represent words and double words as concatenations of smaller values, so whatever our most granular value is. The logic or whatever you express these in, we'll get to later. It's basically a way of expressing the execution of a program such that it can be fed to a solver. We then express, by traversing the graph, we can express the additions simply as an assignment of the result of an addition operator, and a subtraction in a similar fashion. And at that point, you can express additions, subtractions, essentially everything that has occurred as something that resembles a logical formula that you may or may not be familiar with. Typically, these formulae that you construct on real programs are like megabytes in size, not things you want to be reading by hand or even dealing with by hand. So we'll get to these, how we actually solve these formulae soon. But first, I want to, I guess, give an example of why they would be useful and what we'd want to do with them. So we typically input a formula with 0 or more unbound variables. So those are variables that don't have a value assigned to them, which we assume that a user can control or an attacker can control. And we expect this solver or black box or whatever to output true if there's an assignment to the unbound variables that makes the formula satisfiable. So that's if you have conditions, these conditions are satisfied. And it will also output an assignment to these variables. So this formula basically, I think, comes from the previous node. So say, for example, we can control an input value. Like 10 functions later, use your imagination, it's quite small. 10 functions later, we have a value assigned to AX. We want AX to be equal to 10. Essentially, passing this off to a solver where there are unbound variables, if you can return a satisfying assignment, it means that it has come up with an input assignment that satisfies all the conditions. So the ands, there'll typically be like other symbols in there as well, so like greater than, less than, equal to, that satisfies all of these conditions which represent the execution of the program, and therefore providing this input value to the actual program should result in the value 10 in AX or whatever. Realistically, doing this in this fashion, oh, sorry, the actual example I gave there is the one for the next slide. In this case, we control an input value. We want to see what the output value is. We simply just set the input value and then see what comes out at the other end. There's no real advantage to doing this over running it on a CPU, because that's essentially what a CPU will do. The next example, which is what I just talked about, is where we specifically set an output value, which in this case is the green. So we set ID 12 to be equal to 10. We will then pass it off to a solver, which will come up with an assignment for ID 0, ID 3, and ID 6, which were AX, BX, and CX in our example, which are unbound variables, that results in a 10 being inserted into ID 12. In this example, it's obviously trivial. You can do it in your head, but if you consider like hundreds of assembly instructions represented in this fashion, it becomes a lot harder to reason backwards yourself, and you can't do this on a CPU, obviously, in terms of just letting the code execute. We typically want to add conditional instructions to this, purely to represent the conditions that are in a program. These are relatively simple to derive. As I said earlier, you record when flags are set, and then when flags are used, you simply express the semantics of, like, if it's a jump greater, then the relationship is that one thing is greater than another, basically. So you do this, you can express this in a formula pretty simply. You just, again, append on the condition. As soon as you look at this, you start to consider what happens if this condition isn't taken, or what happens on the other side of that, that jump, which is basically one of the major downfalls, I guess, of dynamic analysis, in that we end up with incomplete transition tables, which basically, in the red in this case, if the red is executed but not the blue, then we have a formula representing one possible path. If we have the blue executed but not the red, then we have a formula representing the other path. And essentially the problem is if we have only one of these formulae, and we try to reason about general cases, so we ask the formula, or if we ask the solver, is it possible for AX to be equal to 10, but the red code is executed, it will say no, whereas obviously it is. So this is something that we need to keep in mind, basically. Again, you can deal with this dynamically by concatenating formulae together and trying to drive the program down as many paths as possible, but it's quite messy. Realistically, at this point, you want to start adding in a static analysis. But if you did want to essentially use dynamic analysis to do this, you can actually use the solver itself to drive execution. Meaning that if you have an input that takes one particular path, and you wanted to take at the last jump, or conditional jump, you want to take it the other branch, you essentially want to generate an input with that condition negated. So typically you do this by appending the negation of the condition onto the formula, passing the formula off to a solver, and then the input generated should theoretically take that path. This has been implemented by Microsoft in particular with their Sage project, so they essentially use it to fuzz code. Basically, if you have an input that drives execution down one particular path, you want to fuzz another path, you just negate conditions and move on. There's also an open source version called FuzzGrind, which does something similar, works on top of Valgrind, and it's worth checking out. So how do we actually solve these formulae? Basically, we have, at this point, a bunch of formulae with constraints, but how do we actually reason about these? Basically, there's a huge amount of academic research on theorem proving, some of it useful, some of it not. But the good side to this is that they also have, I guess, an appreciation for the practical side of the theory, in that every year they essentially hold a competition whereby they get all the solvers that they want to enter into this competition, provide them with like hundreds of examples, and then rank them based on how good they do. They all take a standard input format, so if you have an input format that works with one solver, it'll work with any other. And basically you can typically download these things and use them in your own code, so you don't need to do any coding once you have a formula, you can just feed them to these things. So I'm very quickly going to go through this. Basically, our formula at the moment might look familiar to some of you that have taken like basic logic courses or whatever. Propositional logic, typically you have punctuation, you have ands, ors, you have implications, you have basic axioms, and then you have transformation rules. You interpret these formulae, basically you can do it using truth tables, which typically just describe what a combination of Boolean variables result in what output value. In terms of truth and satisfiability, so you can see that this kind of looks similar to what we were talking about earlier in terms of the formulae built from the data flow graph. How do you decide whether a particular assignment to these variables is satisfiable, and more importantly, how do you get a satisfiable assignment from the solver so you don't have to figure it out for yourself? The basic approach is truth tables. Unfortunately, there's 2 to the power of n different interpretations, so you would essentially end up running through something like this, building a truth table for a realistic formula where you have thousands of variables, thousands of clauses, is quickly going to become, I guess, unwieldy. So the standard, or I guess one of the more common algorithms for actually doing this on a large, massive scale, essentially what you have here is you have a massive state space search. So you're looking for an assignment to input variables that result in a true in the final column. It's called the DPLL algorithm. Basically, it's just a massive search through a huge state space. They never actually explicitly represent the entire formula. Realistically, if you want to use these tools, you don't need to know a whole lot about this. You can treat it like a black box. But the main issue is that our formula is quite obviously not in propositional logic. So we have a propositional skeleton in terms of we have AND, we may have ORs, that kind of stuff. But to express things like addition, subtraction, multiplication, we tend to need a higher order language or logic. This is where SMT solvers come in, which basically take a core SAT solver, they combine it with theory-specific solvers for addition, or not addition, for linear or for arithmetic, and allow us to express more interesting properties. So if you had to express this in propositional logic, one, I'm not sure if you could, and two, it would look a lot more messy. So the SMT solvers, basically the theory-specific solvers, allow us to deal with more realistic problems, such as the semantics of real-world assembly code. At this point, assuming that I haven't moved too fast or under-explained a lot of things, we're at a point where we can take an executing program with something like Pin or Dynamo Rio. We can instrument it. We can then do syntactic transformations. We can then apply our applications or instruction semantics to a basic model that we have in memory. We can query this model to build formulae, and we can then express these formulae in terms of this SMT-lib format, which is accepted by any decent solver. And then we can solve these formulae, basically to drive program execution, to get an understanding about or an intuition for what a piece of code actually does. Or if we don't actually want to go to the hassle of reverse engineering huge chunks of code, we can do like the previous example and simply restrict output variables in this input formula and just ask the solver what are the input variables needed to give this output. This is essentially what SMT-lib format looks like for that thing at the top. Typically, you will just write a library to convert a graph into this formula. You don't want to be writing these by hand. And this is typically what it will give you back. So it'll give you, this is the ISIS solver. It'll give you back a chunk of bit vectors, basically, just values expressed, ones and zeros. You can then interpret that as an input assignment. How this is actually useful for exploit development. Am I over time, or? Okay, cool, I'll try and hurry up. How this is useful for exploit development. Basically, we can use the data flow analysis and taint analysis to do quite a lot of stuff without even involving the theorem proving side. So you can tell if you have an access violation on a read or a write. You can tell if you've been tracing all executed instructions, if these have been directly derived from user input. And by directly derived, I mean derived via like additions, mulls, subtractions, whatever have you. We can run into, I guess, false positives in this case, in that sometimes it is viable for a read or a write to actually be tainted in some way by user input, but it might be constrained, like the bounds, so you might have, the offset might be constrained to be plus 10 from a base. So you can typically actually let a solver take care of this for you in terms of, you can ask it what are the bounds on this constraint. So if you have a 4-byte value, you can say, give me back an expression of all of the conditions that have been imposed on this 4-byte value. If there are none, then you know it's completely under your control. If there are some, you can then ask it for sample values from this range, at which point you can start trying to figure out for yourself whether you can write or read from sensitive memory locations. As for EIP, typically if you've got a user-controlled byte in EIP, something's gone hilariously wrong. So that's, I guess, the trivial case. In terms of locating potential shellcode buffers, if you can, again, track all memory, or at any point in program's execution, if you can figure out all memory locations controlled by user input or whatever, basically you have a complete set of, at that point, the usable locations for shellcode, or for shellcode, assuming you're not doing something more complicated. This is pretty easy to do. I mean, if you're doing by hand and you input like 1,000 A's, you can scan for like 1,000 A's in memory. But even if every A has like 1 added to it, that method quickly falls down, but obviously it's still a viable shellcode buffer. Also, if you have, say, 1,000 A's in memory, and you look at that 1,000 A's in your debugger, you have no idea of the actual conditions that have been imposed on that. So throughout the entire program's execution, they could have restricted every single one of those bytes to only ever contain the value A. And without considerable RE effort, that's quite hard to actually enumerate. Whereas if you have a graph representing everything that's actually been done to those bytes, then it's a simple query. And it's essentially an instant operation. To actually undo mangling of shellcode, so again, the case of where if you have a loop that takes an input, there's some arithmetic relationship between the input and the output. Actually finding those buffers in memory can sometimes be a bit annoying, but you can typically just use a solver to undo that kind of mangling, as long as there aren't obviously branches that you don't know about, which can happen. So in this case, if you have an add 4 and you pass this off to a solver where your output constraints are that the output should look like my shellcode, whatever bytes it happens to be, your solver will give you back every byte in the shellcode minus 4, which when passed through this mangling loop will obviously equal your output shellcode. And there's a small subset of exploits that you can express almost the entirety of the exploits in terms of constraints. So you can constrain read and write addresses. You can constrain the shellcode. You can constrain other values in memory such that the paths you want to take are actually executed, and then have the solver automatically generate the entirety of the input that you need to provide to the solver to gain EIP control. That's essentially what my dissertation was about, my master's thesis. It is a pretty small subset of exploits, realistically speaking. And in the real world, like the actual stuff that you can use this for tends to be the 3 previous cases. So it's more assisting a human rather than replacing them. So conclusion time. Summary, basically, I think we can do better as a community in terms of the tools that we have, in terms of assisting, just making our day-to-day lives a little bit easier, removing a little bit of the mundanity from it. These tools aren't hard to build. A full proper retained analysis tool, it was like 12,000 lines of C++, which isn't a lot. In terms of actually understanding code, understanding semantics, understanding what things do, we haven't really come very far, I don't think, in terms of tool development. It still tends to be quite internalized in our skill sets, and I think it's something that we can probably do better with. In terms of the actual summary of this talk, basically, tracking tainted data, we can find shellcode buffers, we can figure out when crashes are actually under our control versus when crashes aren't under our control. By adding formula solving onto this, we can essentially treat chunks of assembly code as a black box in terms of just manipulating input values to provide output values. Typical annoyances, dynamic data flow analysis tends to be quite slow. So opening a PDF file in Reader, if you're doing full instrumentation, can take you anything from like 10 minutes to an hour and a half, which is fine if you get good output from it, but sometimes if you're impatient by nature, it can get annoying. And Internet Explorer, again, more fun. By its nature, we get an incomplete picture of the actual executed, or of the potential executed code. So you can never really conclude from purely dynamic analysis that an exploit or a potential exploit of vulnerability is or isn't possible, and realistically, you wouldn't want to try to do that. Theorem proving itself, if you want to use a theorem prover as a fuzzer, for example, to drive input and solve real conditions in real programs, there are cases where it can take hours for it actually to provide you with a satisfying input. Typically for small chunks of assembly code, which is what I prefer to use it for, so just analyzing like a single function, you get instant results. But for an entire application, it can take a bit longer. In terms of infrastructure, this is basically what I was talking about. There isn't a huge, there are basic building blocks. So we have PIN, we have Dynamo Rio. For building static analysis tools, you have, there's Vine and BAP, which come from research groups, and there's also, you can build static analysis tools on top of BinNavi. But there isn't a huge amount of documentation on how to do this or a huge amount of open source code on which to base your tools on. So future work, basically I would like to get this stuff from essentially a command line tool, which it is at the moment, into a GUI that we can integrate with our day-to-day workflow or whatever. Integration with static analysis toolkits I think is quite important for dynamic analysis. You can optimize your dynamic analysis with static analysis by computing summaries of code so you don't actually need to analyze them at runtime. And likewise, you can make static analysis more precise with dynamic analysis. And hopefully, I mean, more useful and ambitious tools in general. I like IDA, I like Community Debugger, I like OllyDBG, but I think we can do better than just staring at assembly dumps. And I know some people are working towards this, which is good. And that's pretty much the end of that. Questions? Anybody?